So welcome everyone to cs231n. I'm super excited to offer this class again for the third time. It seems that every time we offer this class, it's just growing exponentially, unlike most things in the world. So this is the third time we're teaching this class. The first time we had 150 students. Last year we had 350 students, so it doubled. This year we've doubled again to about 730 students when I checked this morning. So anyone who was not able to fit into the lecture hall, I apologize. But the videos will be up on the SCPD website within about 2 hours. So if you weren't able to come today, then you can still check it out within a couple hours. So this class, cs231n, is really about computer vision. And what is computer vision? Computer vision is really the study of visual data. Since there's so many people enrolled in this class, I think I probably don't need to convince you that this is an important problem, but I'm still going to try to do that anyway. So the amount of visual data in our world has really exploded just to a ridiculous degree in the last couple of years. And this is largely a result of the large number of sensors in the world. So all of us are, probably most of us in this room are carrying around smartphones, and each smartphone has 1, 2, or maybe even 3 cameras on it. So I think on average, there's even more cameras in the world than there are people. And as a result of all these sensors, there's just a crazy, large, massive amount of visual data being produced out there in the world each day. So one statistic that I really like to kind of put this in perspective is a 2015 study from Cisco that estimated that by 2017, which is where we are now, that roughly 80% of all traffic on the internet would be video. So this is not even counting like all the images and other types of visual data on the web, but just from a pure like number of bits perspective, the majority of bits flying around the internet are actually visual data. So it's really critical that we develop algorithms that can utilize and understand this data. However, there's a problem with visual data, and that's that it's really hard to understand. Sometimes we call visual data the dark matter of the internet, in analogy with dark matter in physics. So for those of you who have heard of this in physics before, dark matter accounts for some astonishingly large fraction of the mass in the universe. And we know about it due to the existence of gravitational pulls on various celestial bodies and whatnot, but we can't directly observe it. And visual data on the internet is much the same, where it comprises the majority of bits flying around the internet, but it's very difficult for algorithms to actually go in and understand and see what exactly is comprising all the visual data on the web. Another statistic that I like is that of YouTube. So roughly every second of clock time that happens in the world, there's something like 5 hours of video being uploaded to YouTube. So if we just sit here and count, 1, 2, 3, now there's 15 more hours of video on YouTube. And there's no, like Google has a lot of employees, but there's no way that they could ever have an employee sit down and watch and understand and annotate every video. So if they want to catalog and serve you relevant videos and maybe monetize by putting ads on those videos, it's really crucial that we develop technologies that can dive in and automatically understand the content of visual data. So this field of computer vision is truly an interdisciplinary field, and it touches on many different areas of science and engineering and technology. So obviously computer vision is the center of the universe, but sort of as a constellation of fields around computer vision, we touch on areas like physics, because we need to understand optics and image formation and how images are actually physically formed. We need to understand biology and psychology to understand how animal brains physically see and process visual information. We, of course, draw a lot on computer science, mathematics, and engineering as we actually strive to build computer systems that implement our computer vision algorithms. So a little bit more about where I'm coming from and about where the teaching staff of this course is coming from. Me and my co-instructor, Serena, are both PhD students in the Stanford Vision Lab, which is headed by Professor Fei-Fei Li. And our lab really focuses on machine learning and the computer science side of things. I work a little bit more on language and vision. I've done some projects in that. And other folks in our group have worked a little bit on the neuroscience and cognitive science side of things. So as a bit of introduction, you might be curious about how this course relates to other courses at Stanford. So we kind of assume a basic introductory level understanding of computer vision. So if you're kind of an undergrad and you've never seen computer vision before, maybe you should have taken cs231n, which was offered earlier this year by Feifei and Juan Carlos Niebles. There was a course taught last quarter by Professor Chris Manning and Richard Socher about the intersection of deep learning and natural language processing. And I imagine a number of you may have taken that course last quarter. But we will cover some of there'll be some overlap between this course and that, but we're really focusing on the computer vision side of things and really focusing all of our motivation in computer vision. Also concurrently taught this quarter is cs231a, taught by Professor Silvio Savarasi. And cs231a really is a more all-encompassing computer vision course. It's focusing on things like 3D reconstruction, on matching and robotic vision, and is a bit more all-encompassing with regards to vision than our course. And this course, cs231n, really focuses on a particular class of algorithms revolving around neural networks and especially convolutional neural networks and their applications to various visual recognition tasks. Of course, there's also a number of seminar courses that are taught, and you'll have to check the syllabus and course schedule for more details on those, because they vary a bit each year. So this lecture is normally given by Professor Feifei Li. Unfortunately, she wasn't able to be here today. So instead, for the majority of the lecture, we're going to tag team a little bit. So she actually recorded a bit of pre-recorded audio describing to you the history of computer vision, because this class is a computer vision course, and it's very critical and important that you understand the history and the context of all the existing work that led us to these developments of convolutional neural networks as we know them today. So for the next 10 minutes or so, I'll let virtual Feifei take over and, and give you a brief introduction to the history of computer vision. And at that point, after about 10 minutes, I'll step back in and continue and finish up the lecture.
So here's the agenda for today. We'll go through a brief history of computer vision, and then Justin and Serena will go over the logistics of cs231n. Speaking of the history of computer vision, let's talk about the history of vision. And I want to take you back 543 million years ago. That's a long time ago. What is so special of that time? Well, that is at the dawn of a very interesting period, geological period on Earth, called the Cambrian explosion period. During the 10 million years between 543 million years and 533 million years, the number of animal species on Earth exploded from just a few species to a lot of different species. Evolutionary biologists call this period the Big Bang of evolution, and it's been always a mystery why the simple organisms that were floating around the ocean suddenly start to speciate and develop all kinds of features and varieties. What was driving this? A lot of studies went into understanding fossils, climate change, just the evolution of the Earth, and so on. But recently, a very important study kind of offered the most convincing explanation. That was by an Australian zoologist called Andrew Parker. Dr. Andrew Parker said that around 540 million years ago, the first animal living in the water, all animals were living in the water, similar to a trilobite, developed the first eyes. And the first eyes of animals are actually really simple, a little bit like pinhole cameras. There's just a hole and that collects some lights. But that changed everything. When the first animals that can see, what happens is that food seeking became a very active activity. You really can just go grab the food that you want to eat. And quickly animals start evolving. There are predators that went after prey, and prey that went around and hide from predators. So animals quickly started differentiating and finding all kind of tricks for themselves. Andrew Parker said, basically the development of the eye set out an evolutionary arms race where animals start to find speciate in order to evolve and keep the species alive. So eyes basically since then has become the most important sensory system of the animals. And for humans, it's the same. We use more than half of our brain in functions related to vision. It is critical for our survival, for our navigation, manipulation, work, entertainment, socialization, and meaning. So the study of vision is very intriguing. So is the replication or the development of visual machines. So let's just fast forward to the first few visual machines that humans have made. Well, even before Christ, there have been people making cameras, but one of the most first sophisticated camera was developed by Leonardo da Vinci. He calls it a camera obscura. This is a device that uses lens and a box to collect light and to record the outside imagery. And since then, the development of the camera has been extremely interesting. And to this day, we all hold a very high quality smartphone that takes amazingly high quality digital pictures. Well, let's look at another milestone in the study of vision, and that is in around 1959 and early 1960s. Neuroscientists Hubel and Wiesel were postdocs in a lab at Harvard. They were studying the mammalian vision system, namely cats. We know by then that there is a primary visual system that all mammals have, and the visual system, but they want to know, what do these neurons do in the primary visual system? That is the first stage that visual information from animal retina arrive, one of the first stages that information from retina arrives at. So after some careful study, Hubel and Wiesel found something really intriguing. There are two important take-home messages. The first important take-home message is that the neurons in the early part of the mammalian visual system respond to simple structures of the environment. And it's not just all simple structure, it's oriented edges. So a neuron in a primary visual cortex will be preferring 30-degree bar. And then another neuron will be preferring a 90-degree bar. And they're organizing in clusters or columns in the primary visual system. And then through these simple receptive fields, that's what they call, the visual systems start to make things more complex. So the second thing Hubel and Wiesel found is that the visual system is organized in a hierarchical way. The receptive fields of neurons go from simple to more complex, and eventually to things like objects. And that has a profound impact in the way computer vision has been thinking about how we should develop computer algorithms. You'll see during the history of computer vision, we have, even though methods have changed for several times, but this idea of using simple structure to build up the visual world hasn't changed, and a lot of that inspiration comes from the neuroscience studies. So, the field of computer vision is a very young one. Some people say that Larry Roberts wrote the first PhD thesis of computer vision, where he looked at a world of very simple geometric shapes. He calls it the block world. And his thesis focuses on developing methods to understand what the orientations of these blocks look like. Another urban legend is that the birth of computer vision can be precisely dated on July 7th, 1966. That's the day that an MIT professor wrote the following memo. And the memo is to propose a summer vision project. In 1966, the field of artificial intelligence was already born. A lot of pioneers were studying how we can make machines intelligent. And vision is clearly part of intelligence, it's part of human intelligence, it's part of some animal intelligence. So clearly, we want to make machines see. But our pioneers underestimated how hard vision is. So, in this summer vision project, the MIT professor proposes that, quote, the summer vision project is an attempt to use our summer workers effectively in the construction of a significant part of a visual system, unquote. So the ambition in that summer was to produce an entire visual system. Of course, even though that set off the goal of building a vision system, it didn't accomplish it. After 50 years, computer vision is one of the healthiest growing subfield of the AI, artificial intelligence, and there's still a lot of problems remain unanswered. So hopefully, throughout this course, you come to appreciate how difficult it is to make a seeing machine. And seeing is not just to take imageries. Seeing is about understanding. And even with today's powerful deep learning algorithms, there is still a lot of seeing problems that we haven't solved. And this field will continue to grow. And I hope that you all will be fascinated by the field of computer vision. An important historical figure to remember in computer vision is David Marr. David Marr passed away in his 30s, very young. But just before he passed away, he published a book called Vision. And in this book, he proposed that we should be seeing vision in several layers. When an image comes in, we should be seeing the image in edges, just like the primary visual cortex that Hubel and Wiesel recorded in cats are telling us. It's the oriented edges that form the basis of the visual world. And then he proposed that the imagery world, is separated into what he calls 2.5D sketch. These are the rough layering of the surfaces and the discontinuities and depth, so that we roughly know what things are in the foreground, what things are in the background. And finally, the completion of the visual task is the full 3D understanding of any objects. And that formed David Marr's concept of vision. That concept has influenced a lot of work in the 70s, 80s, and 90s. One of the pioneering work in the 70s are done actually in Palo Alto, both at Stanford as well as at Stanford Research Institute, SRI. In this work, one is called generalized cylinder, another one is called pictorial structure. The researchers, pioneers, were thinking of how to model the building blocks of the visual world namely objects. And the idea is that objects are made of small, simpler parts, either generalized geometric shapes or generalized cylinders, or just parts like for a human face, eyes, ears, and mouth. And then it's the configuration that of different parts that give meaning to different objects.
All right. Thanks so much, Feifei. I think that I'll take it over from here. So the next really important work that I want to cover. Oh, OK. All right. Is this one working? OK. So I think that the next really important work that I want to cover in the history of computer vision is the work of David Lowe. And David Lowe is another one of these towering figures in the history of computer vision. So one of his early works was based on this idea of finding objects in images. So and this is really based on this intuition from Hubel and Wiesel that the primary way that the visual cortex recognizes objects and images is through edges. So the idea was that in an image like this, where we want to find all the coins in the image, we might start with some template for what the object looks like. For example, we know that the coin is a circle, and we know what the edges of that coin are supposed to look like. So then, given this template for the object, we can first compute the edges of the image, then match the coin into the diagram, into the edge image, and in this way, we can now recognize coins in the image. This is a little bit of a silly toy example, but in the paper, he has a much more impressive example, which is a whole pile of disposable razors. So those have kind of this funny geometric shape, but if you know the shape ahead of time, then you can try to match the razor into the edges of the image, and in that way reconstruct the 3D pose of all the objects in the scene. But around that time, actually, it's important to remember that digital images and digital cameras were a relative rarity back in the 80s. And a lot of the work that was happening around that time was relatively these small toy examples with pictures of coins or razors. And this showed tremendous progress. This showed that a lot of these ideas probably would eventually pan out and give us something amazing. But it was really in the 90s that people started to try and scale up to more realistic scenes, more realistic images, as things like digital cameras and computers and the internet started to become much more popular. So there was sort of another interesting shift in computer vision that happened around this time. And that was maybe moving a slight bit away from this idea of 3D reconstruction. Remember, David Marr told us that the ultimate goal of computer vision was to reconstruct the 3D geometry of the world around us, given this ambiguous two-dimensional image. But now in the 90s, this idea of perceptual grouping and segmentation became very popular. Here the idea is that rather than trying to reconstruct the whole 3D scene instead we just want to group pixels into semantically related parts and say that maybe these orange pixels all belong to one object, these brown pixels belong to another object, and that maybe we have this pipeline where first we group pixels according to their semantics, and then it might become easier to recognize what the objects are once we have this perceptual grouping down. So one of the landmark works in sort of this vein of research came from Jitendra Malik, who's now a professor at UC Berkeley, called Normalized Cuts. So this is one of these very important works that attempted to do this idea of perceptual grouping. And one thing I'd like to point out is that even though this problem of perceptual grouping seems relatively straightforward, even today with all our powerful giant neural networks, we still don't even have this very basic problem perfectly solved. So there are definitely corner cases that remain unsolved and remain challenging for algorithms even today. So another landmark work in the history of computer vision that you may have seen before is this work from Viola and Jones on face detection. So here the idea is that given an input image, we want to draw boxes around all of the faces in that image. And this work is really critically important for a couple different reasons. One, you can see that it recognizes faces in terms of these patterns of adjacent color. So this is really inspired by this idea from Hubel and Wiesel, again, that the primary, like the first thing that should happen in your brain or in your computer system for recognizing images is this notion of sort of local patches, local variations between light and dark in different orientations. So this Viola-Jones algorithm is really building upon that, and that's really interesting. Another point about Viola and Jones is that it was one of the first to really incorporate learning into this concept of vision. So here in Viola and Jones, we have some training data of example images with the boxes of the faces already drawn. And there is some learning process where the algorithm decides how best to combine these little edge-like features in order to recognize faces. So this idea of learning became super critical and super important in computer vision. And the learning algorithm that they were using is quite a bit different than those we use now. But this idea of learning from data is super critical. And that's something that we'll really investigate throughout the course of the quarter. A third point about this algorithm, which is really interesting, is that I think it was one of the first that really made the jump quite quickly from research to application. So this paper was published in 2001. And I believe by 2006, there were already commercial applications of this algorithm deployed in digital cameras that could now, I don't know if you remember digital cameras of that era, but you could often hold them up and hold down the shutter button halfway, and it would detect the faces and maybe use that to determine where in the image to focus. And that was pretty remarkable at that time, that this sort of research algorithm could jump out of the lab and into production in just a short number of years. So, of course, nowadays, that cycle is much accelerated, but at the time, this only 5-year gap was quite remarkable. So probably one of the most famous papers in computer vision is this, again from David Lowe, I told you he was an important guy, was this SIFT algorithm from 1999. So this is probably one of the most cited papers in computer vision and perhaps even in all of computer science. And the idea is, again, about matching, somewhat similar to his previous work, where suppose that we have this picture of a stop sign, and now we want to use this picture of a stop sign to recognize other stop signs in other images, even if they're from different angles. And the critical idea here was twofold. One is this idea of recognizing key points. So we'll sort of identify in the image some set of points which are easily identifiable because they lie near corners or other such things. And now for each of those key points, we'll generate a short 128-dimensional vector that describes the visual appearance of the image around that key point. And this idea of using vectors to describe images is something that follows through all of computer vision and is something we'll revisit over and over again throughout the course. So at this time, the way they were computing these vectors was sort of based on these local edges, again from Hubel and Wiesel, and then introducing a little bit of invariance to slight changes in angle or orientation or position, and then eventually combining all this stuff together, giving us edges, giving us invariance, and eventually giving a vector to describe the appearance of this local image patch. And now at test time, when you want to now recognize this stop sign, you kind of do this process in reverse, where we detect the stable key points on the second image, and now try to match these vectorial descriptors from our database image on the left and our test image on the right. And this was just this was a super well-known paper, and this got used all over the place, probably in the era, maybe in the late 90s for about 10 years after that. And this idea of coming up with clever ways of writing down vectorial representations of images and of patches was something that was hugely popular during this time. So people spent a lot of effort trying to come up with very clever ways for writing down different vectorial ways of describing the appearance of images. And so for this example, in spatial pyramid matching, they designed a mechanism for describing whole images that could be used for scene recognition. And this sort of feature vector then gets fed into some downstream machine learning algorithm, which then learns to classify based on the feature vectors. And another work from around this era is this idea of histograms of oriented gradients, which was another of these feature descriptors which was developed for detecting objects in images. Building on this was the deformable parts model, which got used for object detection a lot at the time. And this actually harkens back to this pictorial structures model that we saw from the 70s, where now we sort of have this concept of a person being represented by this overall template of gradients, as well as little tiny templates for the arms and the head and the different parts of the object. And these parts are allowed to deform a little bit away from their canonical positions. And they use sort of what's called a latent SVM formulation. I don't want to get into the details here, to actually learn this thing and recognize it in images. It was also around this time that the community really started to focus on the importance of data and the importance of standardized benchmarks. So what happened a lot around this time was that people who were working in computer vision would download some images, create some data set, create some algorithm, and show that it works on their data set. But it was really hard to determine actually whose algorithm is working better and actually track the progress of the field. So starting in the early 2000s, this European group built this Pascal VOC data set. So this comprised about tens of thousands of images, and each image was annotated with 20 object categories. These were things like trains and people and airplanes and dogs and horses and stuff like that. And the goal was that, and the idea was that every year they would hold a challenge where different teams across the world would submit the results of their algorithm on this standard benchmark, and this would allow us to track the progress of the field going forward. And as you can see here on the right, from about 2006 to 2012, the field of computer vision made very steady progress on this benchmark. And this idea of benchmarking as a way to measure the success of computer vision is something that has continued to this day. So some of you may have heard of the ImageNet dataset. This is sort of in some sense, the spiritual successor to Pascal VOC. So Pascal VOC had tens of thousands of images, 20 object categories. That was great. It let us benchmark where we were and how we were progressing. But the world has a lot more than just 20 object categories, I think. And this ImageNet project, which was initiated by Feifei and other students in the lab at that time, was an attempt to solve this problem. So they collected a massive number of images, around 14 million images, annotated with 22,000 object categories. And I promise you, it wasn't grad students who labeled all these things. That would have taken a while. They used Amazon Mechanical Turk to crowdsource this over workers on the internet to collect many annotations of many images. This was hugely influential. This was orders of magnitude bigger than the Pascal VOC that we saw on the previous slide. And sort of inspired by Pascal VOC, Feifei and collaborators run every year this ImageNet Large-Scale Visual Recognition Challenge, which has sometimes been called the Olympics of Computer Vision. That's very cool. And sort of the premier event of these Olympics is the Image Classification Challenge. So here the setup is that there's roughly 1.5 million training images and 1,000 different object categories. And the algorithm needs to look at an image and determine which of its categories it is. And this is a pretty challenging problem because these images because there's a lot of different categories to recognize. There could be a lot of variation within classes and between classes. Also, many of these categories are very fine-grained. Something like individual dog breeds might be one of these 1,000 categories. So this is an extremely challenging problem. And over the course of the ILS VRC challenge, which was first ran in 2010, the field has made just tremendous, remarkable progress on this benchmark data set. So the first two times this challenge was run, in 2010 and in 2011, this was before the advent of deep learning. These methods were based on still ideas of hierarchy and local features and machine learning. A lot of these core crucial ideas that have been important throughout the entire history of computer vision. But their absolute performance left a little bit to be desired, was a little bit lacking. And now the sort of breakthrough moment for deep learning happened in 2012, when you see this gigantic increase in accuracy from 2011 of 25.8% all the way down to 16.4% in 2012. And the difference there was a large convolutional neural network trained end-to-end on this data set. And after 2012, the entire field switched over to convolutional neural networks, at least for this problem of image classification. And every year in 2011, 2014, 2015, 2016, the error rate has just gone marching down and down and down and down. And actually, the 2015 challenge, we hit about 3.57% accuracy, which by some accounts is perhaps better than even humans on this task. So there was a very famous, actually the benchmark human in this task was Andrei Karpathy, who was a former instructor of this class. I think he's floating around somewhere here. So that was our brief introduction to computer vision and the history of computer vision. So what we're hoping is that when you come out of this course, you're not thinking of yourself as a machine learning practitioner or a deep learning practitioner. We also want you to think of yourself as a student of computer vision. Because even though we have these amazing tools like convolutional neural networks and deep learning and all this amazing stuff, it's still important to understand that these ideas did not develop in a vacuum. They are building upon a rich history of a long body of work in computer vision when many people were trying to attack many different problems. And as we move forward and in the field and try to tackle even bigger and larger and more impressive problems in computer vision, I think it's very likely that we'll need to look back to these older works for inspiration as we try to tackle these larger and larger problems. So now I want to shift gears a little bit and talk a little bit more about this class, cs231n. So this class focuses on the primary focus of this class is this image classification problem, which we previewed a little bit in the context of the ImageNet challenge. So in image classification, again, the setup is that your algorithm looks at an image and then picks from among some fixed set of categories to classify that image. And this might seem like somewhat of a restrictive or artificial setup, but it's actually quite general. And this problem can be applied in many different settings, both in industry and academia and many different places. So for example, you could apply this to recognizing food or recognizing calories in food or recognizing different artworks, different products out in the world. So this relatively basic tool of image classification is super useful on its own and could be applied all over the place for many different applications. But in this course, we're also going to talk about several other visual recognition problems that build upon many of the tools that we develop for the purpose of image classification. We'll talk about other problems such as object detection or image captioning. So the setup in object detection is a little bit different. Rather than classifying an entire image as a cat or a dog or a horse or whatnot, instead we want to go in and draw bounding boxes and say that there is a dog here and a cat here and a car over in the background, and draw these boxes describing where objects are in the image. We'll also talk about image captioning, where given an image, the system now needs to produce a natural language sentence describing the image. It sounds like a really hard, complicated, and different problem, but we'll see that many of the tools we develop in service of image classification will be reused in these other problems as well. So we mentioned this before in the context of the ImageNet challenge, but one of the things that's really driven the progress of the field in recent years has been this adoption of convolutional neural networks, or CNNs, or sometimes called ConvNets. So if we look at the algorithms that have won the ImageNet challenge for the last several years, in 2011, we see this method from Lin et al., which is still hierarchical. It consists of multiple layers. So first we compute some features. Next we compute some local invariances, some pooling, and go through several layers of processing, and then finally feed this resulting descriptor to a linear SVM. What you'll notice here is that this is still hierarchical. We're still detecting edges. We're still having notions of invariance. And many of these intuitions will carry over into ConvNets. But the breakthrough moment was really in 2012 when Jeff Hinton's group in Toronto, together with Alex Krichevsky and Ilya Sutskever, who were his PhD students at that time, created this 7-layer convolutional neural network, now known as AlexNet, then called Supervision, which just did very, very well in the ImageNet competition in 2012. And since then, every year, the winner of ImageNet has been a neural network. And the trend has been that these networks are getting deeper and deeper each year. So AlexNet was a 7 or 8-layer neural network, depending on how exactly you count things. In 2015, we had these much deeper networks, GoogleNet from Google, and VGG, the VGG network from Oxford, which was about 19 layers at that time. And then in 2015, it got really crazy. And this paper came out from Microsoft Research Asia called Residual Networks, which were 152 layers at that time. And since then, it turns out you can get a little bit better if you go up to 200, but you run out of memory on your GPUs. So We'll get into all of that later. But the main takeaway here is that convolutional neural networks really had this breakthrough moment in 2012. And since then, there's been a lot of effort focused on tuning and tweaking these algorithms to make them perform better and better on this problem of image classification. And throughout the rest of the quarter, we're going to really dive in deep, and you'll understand exactly how these different models work. But one point that's really important is that it's true that the breakthrough moment for convolutional neural networks was in 2012, when these networks performed very well on the ImageNet challenge. But they certainly weren't invented in 2012. These algorithms had actually been around for quite a long time before that. So one of the sort of foundational works in this area of convolutional neural networks was actually in the 90s from Jan LeCun and collaborators, who at that time were at Bell Labs. So in 1998, they built this convolutional neural network for recognizing digits. They wanted to deploy this and be able to automatically recognize handwritten checks or addresses for the post office. And they built this convolutional neural network, which could take in the pixels of an image and then classify either what digit it was or what letter it was or whatnot. And the structure of this network actually looks pretty similar to the AlexNet architecture that was used in 2012. Here we see that we're taking in these raw pixels. We have many layers of convolution and subsampling together with these so-called fully connected layers, all of which will be explained in much more detail later in the course. But if you just kind of look at these two pictures, they look pretty similar. And this architecture in 2012 sort of has a lot of these architectural similarities that are shared with this network going back to the 90s. So then the question you might ask is, OK, if these algorithms were around since the 90s, why have they only suddenly become popular in the last couple of years? And there's a couple really key innovations that happened that have changed since the 90s. One is computation. Thanks to Moore's law, we've gotten faster and faster computers every year. And this is kind of a coarse measure, but if you just look at the number of transistors that are on chips, then that has grown by several orders of magnitude between the 90s and today. We've also had this advent of graphics processing units, or GPUs, which are super parallelizable and ended up being a perfect tool for really crunching these computationally intensive convolutional neural network models. So just by having more compute available, it allowed researchers to explore with larger architectures and larger models, and in some cases just increasing the model size, but still using these kind of classical approaches and classical algorithms tends to work quite well. So this idea of increasing computation is super important in the history of deep learning. I think the second key innovation that changed between now and the 90s was data. So these algorithms are very hungry for data. You need to feed them a lot of labeled images and labeled pixels for them to eventually work quite well. And in the 90s, there just wasn't that much labeled data available. This was, again, before tools like Mechanical Turk, before the internet was super, super widely used, and it was very difficult to collect large, varied data sets. But now, in the 2010s, with data sets like Pascal and ImageNet, there existed these relatively large, high-quality labeled data sets that were, again, orders of magnitude bigger than the data sets available in the 90s. And these much larger data sets, again, allowed us to work with higher capacity models and train these models to actually work quite well on real-world problems. But the critical takeaway here is that convolutional neural networks, although they seem like this sort of fancy new thing that's only popped up in the last couple of years, that's really not the case. And these class of algorithms have existed for quite a long time in their own right as well. Another thing I'd like to point out is that in computer vision, we're in the business of trying to build machines that can see like people. And people can actually do a lot of amazing things with their visual systems. When you go around the world, you do a lot more than just drawing boxes around the objects and classifying things as cats or dogs. Your visual system is much more powerful than that. And as we move forward in the field, I think there's still a ton of open challenges and open problems that we need to address. And we need to continue to develop our algorithms to do even better and tackle more ambitious problems. Some examples of this are going back to these older ideas, in fact. Things like semantic segmentation or perceptual grouping, where rather than labeling the entire image, we want to understand for every pixel in the image, what is it doing? What does it mean? And we'll revisit that idea a little bit later in the course. there's definitely work going back to this idea of 3D understanding, of reconstructing the entire world. And that's still an unsolved problem, I think. There are just tons and tons of other tasks you can imagine. For example, activity recognition. If I'm given a video of some person doing some activity, what's the best way to recognize that activity? And that's quite a challenging problem as well. And then as we move forward with things like augmented reality and virtual reality, and as new technologies and new types of sensors become available, I think we'll come up with a lot of new, interesting, hard, and challenging problems to tackle as a field. So this is an example that is from some of my own work in the Vision Lab on this data set called Visual Genome. So here the idea is that we're trying to capture some of these intricacies in the real world. And rather than maybe describing just boxes, maybe we should be describing images as these whole large graphs of semantically related concepts that encompass not just object identities, but also object relationships, object attributes, actions that are occurring in the scene. And this type of representation might allow us to capture some of this richness of the visual world that's left on the table when we're using simple classification. This is by no means a standard approach at this point, but just kind of giving you this sense that there's so much more that your visual system can do that is maybe not captured in this vanilla image classification setup. So I think another really interesting work that kind of points in this direction actually comes from Feifei's grad school days when she was doing her PhD at Caltech with her advisors there. In this setup, they stuck people and they showed people this image for just half a second. So they flashed this image in front of them for just a very short period of time. And even in this very, very rapid exposure to an image, people were able to write these long descriptive paragraphs, giving a whole story of the image. And this is quite remarkable if you think about it. That after just half a second of looking at this image, a person was able to say that this is some kind of a game or fight. Two groups of men. The man on the left is throwing something outdoors because it seems like I have an impression of grass, and so on and so on. And you can imagine that if a person were to look even longer at this image, they could write probably a whole novel about like who these people are and why are they in this field playing this game. And they could go on and on and on, roping in things from their external knowledge and their prior experience. And this is, in some sense, the holy grail of computer vision, to sort of understand the story of an image in a very rich and deep way. And I think that despite the massive progress in the field that we've had over the past several years, we're still quite a long way from achieving this holy grail. Another image that I think really exemplifies this idea actually comes again from Andrei Karpathy's blog, is this amazing image. So many of you smiled, many of you laughed. I think this is a pretty funny image. But why is it a funny image? Well, we've got a man standing on a scale, and we know that people are kind of self-conscious about their weight sometimes, and scales measure weight. And then we've got this other guy behind him pushing his foot down on the scale, and we know that because of the way scales work, that will cause him to have an inflated reading on the scale. But there's more. We know that this person is not just any person. This is actually Barack Obama, who was at the time president of the United States, and we know that presidents of the United States are supposed to be respectable politicians that are probably probably not supposed to be playing jokes on their compatriots in this way. We know that there's these people in the background that are laughing and smiling, and we know that that means that they're understanding something about the scene. We have some understanding that they know that President Obama is this respectable guy who is looking at this other guy. Like, this is crazy. Like, there's so much going on in this image. And our computer vision algorithms today are actually a long way, I think, from this true deep understanding of images. So I think that despite the massive progress in the field, we really have a long way to go. To me, that's really exciting as a researcher, because I think that we'll have just a lot of really exciting, cool problems to tackle moving forward. So I hope at this point I've done a relatively good job to convince you that computer vision is really interesting, it's really exciting. It can be very useful. It can go out and make the world a better place in various ways. Computer vision could be applied in places like medical diagnosis and self-driving cars and robotics and all these different places, in addition to sort of tying back to this core idea of understanding human intelligence. So to me, I think that computer vision is this fantastically amazing, interesting field, and I'm really glad that over the course of the quarter, we'll get to really dive in and dig into all these different details about how these algorithms are working these days. So that's sort of my pitch about computer vision and about the history of computer vision. I don't know if there's any questions about this at this time. OK. So then I want to talk a little bit more about the logistics of this class for the rest of the quarter. So you might ask, who are we? So this class is taught by Feifei Li, who's a professor of computer science here at Stanford, who's my advisor, and director of the Stanford Vision Lab and also the Stanford AI Lab. The other two instructors are me, Justin Johnson, and Serena Young, who's up here in the front. We're both PhD students working under Feifei on various computer vision problems. And we have an amazing teaching staff this year of 18 TAs so far, many of whom are sitting over here in the front. These guys are really the unsung heroes behind the scenes, making the course run smoothly, making sure everything happens well. So be nice to them. I think I also should mention that this is the third time we've taught this course, and it's the first time that Andrei Karpathy has not been an instructor in this course. He was a very close friend of mine. He's still alive. He's OK. Don't worry. But he graduated, and so he's actually here, I think, hanging around in the lecture hall. So a lot of the development and the history of this course is really due to him working on it with me over the last couple of years. So I think you should be aware of that. Also about logistics, probably the best way for keeping in touch with the course staff is through Piazza. You should all go and sign up right now. And Piazza is really our preferred method of communication with the class, with the teaching staff. If you have questions that you're afraid of being embarrassed about asking in front of your classmates, go ahead and ask anonymously, or even post private questions directly to the teaching staff. So basically, anything that you need should ideally go through Piazza. We also have a staff mailing list, but we ask that this is mostly for sort of personal, confidential things that you don't want going on Piazza. Or if you have something that's super confidential, super personal, then feel free to directly email me or Feifei or Serena about that. But for the most part, most of your communication with the staff should be through Piazza. We also have an optional textbook this year. This is by no means required. You can go through the course totally fine without it. Everything will be self-contained. This is sort of exciting because it's maybe the first textbook about deep learning that got published earlier this year. By Ian Goodfellow, Yoshua Bengio, and Aaron Corville. I put the Amazon link here in the slides. You can go get it if you want to. But also, the whole content of the book is free online, so you don't even have to buy it if you don't want to. So again, this is totally optional, but we'll probably be posting some readings throughout the quarter that give you an additional perspective on some of the material. So our philosophy about this class is that you should really understand the deep mechanics of all of these algorithms. You should understand at a very deep level exactly how these algorithms are working, like what exactly is going on when you're stitching together these neural networks. How do these architectural decisions influence how the network is trained and tested and whatnot and all that. And throughout the course, through the assignments, you'll be implementing your own convolutional neural networks from scratch in Python. You'll be implementing the full forward and backward passes through these things. And by the end, you'll have implemented a whole convolutional neural network totally on your own. I think that's really cool. But we're also kind of practical. And we know that in most cases, people are probably not writing these things from scratch. So we also want to give you a good introduction to some of the state-of-the-art software tools that are used in practice for these things. So we're going to talk about some of the state-of-the-art software packages like TensorFlow, Torch, PyTorch, all these other things. And I think you'll get some exposure to those on the homeworks and definitely through the course project as well. Another note about this course is that it's very state-of-the-art. I think it's super exciting. This is a very fast-moving field. As you saw, even these plots in the ImageNet challenge, basically there's been a ton of progress since 2012. And while I've been in grad school, the whole field is sort of transforming every year. And that's super exciting and super encouraging. But what that means is that there's probably content that we'll cover this year that did not exist the last time this course was taught last year. I think that's super exciting, and that's one of my favorite parts about teaching this course, is just roping in all these new scientific, hot-off-the-presses stuff, and then being able to present it to you guys. We're also sort of about fun, so we're gonna talk about some interesting, maybe not so serious topics as well this quarter. Including image captioning is pretty fun, where we can write descriptions about images. But we'll also cover some of these more artistic things, like Deep Dream here on the left, where we can use neural networks to hallucinate these crazy psychedelic images. And by the end of the course, you'll know how that works. Or on the right, this idea of style transfer, where we can take an image and render it in the style of famous artists like Picasso or Van Gogh or whatnot. And again, by the end of the quarter, you'll see how this stuff works. So the way the course works is that we're going to have 3 problem sets. The first problem set will probably be out later, will hopefully be out by the end of the week. We'll have an in-class written midterm exam. And a large portion of your grade will be the final course project, where you'll work in teams of 1 to 3 and produce some amazing project that will blow everyone's minds. We have a late policy, so you have 7 late days that you're free to allocate among your different homeworks. These are meant to cover things like minor illnesses or traveling or conferences or anything like that. If you come to us at the end of the quarter and say that, oh, I suddenly have to go give a presentation at this conference, that's not going to be OK. That's what your late days are for. That being said, if you have some very extenuating circumstances, then do feel free to email the course staff if you have some extreme circumstances about that. Finally, I want to make a note about the collaboration policy. As Stanford students, you should all be aware of the honor code that governs the way that you should be collaborating and working together. And we take this very seriously. We encourage you to think very carefully about how you're collaborating and making sure it's within the bounds of the honor code. So in terms of prerequisites, I think the most important is probably a deep familiarity with Python, because all of the programming assignments will be in Python. Some familiarity with C or C++ would be useful. You will probably not be writing any C or C++ in this course, but as you're browsing through the source code of these various software packages, being able to read C++ code at least is very useful for understanding how these packages work. We also assume that you know what calculus is, you know how to take derivatives, all that sort of stuff. We assume some linear algebra, that you know what matrices are and how to multiply them and stuff like that. So I don't want to teach you, we can't be teaching you how to take like derivatives and stuff. We also assume a little bit of knowledge coming in of computer vision, maybe at the level of cs131 or 231a. If you have taken those courses before, you'll be fine. If you haven't, I think you'll be OK in this class, but you might have a tiny bit of catching up to do, but I think you'll probably be OK. Those are not super strict prerequisites. We also assume a little bit of background knowledge about machine learning, maybe at the level of cs229. But again, I think really important key fundamental machine learning concepts will reintroduce as they come up and become important. But that being said, a familiarity with these things will be helpful going forward. So we have a course website. Go check it out. There's a lot of information and links and syllabus and all that. And I think that's all that I really want to cover today. And then later this week, on Thursday, we'll really dive into our first learning algorithm and start diving into the details of these things.